Hi everyone. Today we're going to talk a little bit about some of the tests that we are starting off with statistics, ranging from chi-square test, which tests for categorical variables, particularly nominal variables, but also some ordinal variables as well. We will be talking about some of the ways of testing differences between groups. So we've talked in class quite a bit about Amazon using A/B testing, and other websites using A/B testing to be able to test whether one format of a website has an impact on a dependent variable versus another format of a website. Let's say they want to make a change in a website and they want to see if it impacts the number of people who actually click into a particular product or click on a particular part of the page, and they want to test to see if it improves the conversion ratio. Then they would have to test the difference between groups, between the people who see web format A and the people who see format B. And if they're testing 6 different formats at a time, well, we can test one test that does all 6 formats, and we can delve in further to see about that. So we're going to start off with chi-square. I'm going to bounce over to my one of my slides, and kind of reiterate a few of the things that we talked about with chi-square. Let me go over to screen share, and then where's my other screen? I'm going to share my entire screen, and bear with me. Okay. So let's start off with a little bit about hypothesis testing, because I had mentioned before that we were going to get into the statistics, but we're not going to look at it from a heavy statistics angle so much as we let SPSS calculate out the statistics for us. And so not only does SPSS calculate statistics for us, but it also gives us p-values, which are in line with levels of significance, which we've talked about previously in terms of null hypothesis testing. So if we're able to use these p-values, it makes it a lot easier for us to interpret what exactly is going on vis-a-vis testing hypotheses. So I have here a slide that is about 7 steps to talk about null hypothesis testing. Okay. The first one is to develop the null and alternate hypotheses from the research questions. We talked previously about the fact that null hypotheses exist for the basis of being disproven, right? They're boring. There's not much going on. We're saying that groups are similar. We're saying that there's no effects of one variable on another variable. We're saying there's no relationship between a variable or between groups. Okay, that essentially is what the null hypothesis is. It means that nothing is going on. It means that the status quo exists, and that's all nice and good, except for the fact that we want to see that, in fact, changing multiple variables does have an impact on sales. That changing multiple variables does affect one group more than it affects another group. We want to see that changing something actually does mean that there's a relationship between 2 variables that we didn't previously think there was a relationship between. So it is important that we have null hypotheses, but we're generally trying to look in terms of the alternate hypothesis. The alternate hypothesis says that groups are not equal, that groups are related in some way, that that the variables do have an impact on dependent variables and so forth. So developing these hypotheses, we said hypotheses are testable statements. Okay, they are things that we go out and collect data and we test to see whether the hypothesis is supported or not. We develop those from the actual questions, right? So a hypothesis is a statement, and a question, well, obviously is a question. So we can develop the null hypothesis both in plain English and also using Greek symbols. And if you recall, that we always are using Greek symbols to make hypotheses about a population, not about a sample. Okay, we use the sample to make inferences about the population, but we always make hypotheses about the population. we've developed a hypothesis and we have the data that we've already collected, the next thing that we need to do is to determine the appropriate test statistic. One of the things that allows us to determine the appropriate test statistic is whether or not we are using categorical variables or we are using continuous variables, okay? Usually if we're using categorical variables, there are limited statistics that we can use. We'll be covering chi-square in a second. Which is one of the reasons why it's easier to use to go out and collect data that has stronger measures. So using continuous data, again, because we can do arithmetic, using continuous data allows us to do more in terms of testing, okay? So once we determine the appropriate test statistic, and I'm just going to bounce forward to a slide over here. Okay, here's one tree that may help you determine which test statistic to use when. And I've highlighted in red some of the statistics that we will be covering in terms of this class. So obviously we're not covering all of the statistics, but we're using a good portion of them. And if you use this tree, it should be helpful to you to be able to determine which test statistic you need to run. So how do you calculate the test statistic? Well, you can use SPSS to do it. I've given a number of resources that are out there on the internet in terms of how to use SPSS. There are certainly some YouTube videos that I have. We'll be doing some stuff in class in terms of tutorial, just to give you a little bit of hands-on. There's a homework assignment where you'd have to use SPSS, and certainly there are some books and other guides to using SPSS that are out there that'll tell you essentially how to point and click to get to the to run the test statistic that you're looking for. So SPSS will calculate test statistics. It will calculate degrees of freedom. It will calculate p-values, which are the levels of significance. And rather than having to go to a table like we used to do, and we would set alpha or a level of significance to for setting type 1 error, rather than having to go find alpha on a table, go determine the critical value, compare the test statistic to the critical value. SPSS and testing in SPSS and other stat software, but we're using SPSS. Testing in SPSS allows us to get the p-value, and it makes it easier because rather than having to find a critical value, we can just use that as a significance level and compare it to the significance level that we are accepting. Okay, so I have here on number 5, if we're using SPSS, we compare the test statistics significant level to alpha. In number 6, we're deciding whether or not we are rejecting or supporting the null hypothesis and thus rejecting or supporting the alternate hypothesis. And this is critical because obviously we're hoping that we can see a supported alternate hypothesis. Okay? Remember, we want to test the null hypothesis to see if there's nothing going on, but that's a boring hypothesis. We want to see that something is going on, that there is a relationship between ad spending and sales, that ad spending does increase sales, that there is a difference between the amount of ads spent on television versus the amount of ads spent on internet radio and their impact on sales. So certainly there is a benefit to looking and focusing more on the alternate hypothesis. So how do we decide what to do with those alternate hypotheses? And I'm going to start framing these things in terms of alternate hypotheses, even though we are going through a few of the things that deal with the null hypothesis. So if the SPSS significance level, if the p-value, if it's significance, there's a column that will read significant, okay, or it'll say sig. If the significance is less than alpha, then that means the test statistic is significant, and therefore we support the alternate hypothesis. So if p value, if the significance value is less than alpha, which we typically set to 0.05, and the reason we typically set it to 0.05 is because it means that if we sample the population 100 times, we would expect to see a similar result 95 out of 100 times. So it's not necessarily saying that we are 95% certain. What it is saying is that 95 out of 100 times we would expect to see similar results. So that in layman's terms is what we're talking about when we talk about p-values and levels of significance. So if the significance is less than 0.05, then that means the test statistic is significant. We would support the alternate hypothesis. If the p-value is greater than alpha, greater than 0.05, then that means the test statistic is non-significant, which means we reject the alternate hypothesis. And by logic, as you see here on the second line, if we reject the alternate hypothesis, then the logic is that we would be supporting the null hypothesis. And then in step 7, we're interpreting the implications of step 6 in strategic terms. So for instance, if we say that a test statistic is significant, if we make a test between two groups and we see that ad spending is significantly higher than in ad spending on internet radio is significantly higher than ad spending on television, then we would want to say that one is significantly higher. Okay, that ad spending on internet radio is significantly higher than television. So we need to say, what does that mean? We need to bring it back to some sort of strategic result. And the strategic result would mean if ad spending on television is higher and is significantly higher, then perhaps we should be spending more on television if that's what our strategy is. Okay, so again, this is where the statistics and the outcome of a statistics can lead you to a decision that is marketing strategy. All right, so I mentioned here again the kind of the tree that would allow us to determine the appropriate statistical procedure. Certainly there are other ways of making this tree. There are tables that you can make. I've seen tables that look at how many, what the dependent variable is it continuous or categorical, then look at how many variables are independent, are they continuous, categorical? So there are other ways of showing this same tree. I like this tree because I think it's kind of a nice little flowchart way to go about making these decisions. If you find another way that works for you, certainly it's beneficial to understand this, because if you understand it, then you can figure out the best way to discuss what your findings are and know which tests that you want to use to describe your data, to test those hypotheses. All right, so let's talk a little bit about the chi-square test, which we had talked about in class, but we're going to continue and just kind of refresh here. Okay. When we use chi-square tests, we're typically analyzing categorical variables. And if you go back for a second to the tree, okay, and we say that the purpose of the statistical analysis is to explore the relationship between variables, we are looking at frequency data. We are looking at one variable where we're a contingency table where we're comparing to a theoretical distribution. So what we're doing is we're saying that we're going out and collecting some data in a sample, and we want to approximate whether the sample will fit what we would hypothesize in the population as a whole. Okay, so we're essentially looking at equal weighted proportions and testing whether our sample fits those proportions. So we call this particular version of the test the goodness of fit test. The other version of the chi-square test, which is the same exact test, is used with two or more variables to test relationships or dependence or independence of variables. So we call that the chi-test square for association, or the chi-test square of independence. As you may guess from the names of the tests, okay, the chi-square goodness of fit null hypothesis is that the data as hypothesized fits, or rather the data in the sample fits the hypothesized data. In the test for association or the test for independence, our null hypothesis would be that two variables are independent of each other. That we have two categorical variables that are independent of each other would suggest that there's no association, that there's no relationship between the two variables. So what we do is we would calculate out a cross-tabulation table, which looks at rows versus columns of variables and the number or frequency of the data in those columns and rows. And then it would again test the proportionality based on an observed or sampled data versus a hypothesized or expected data, okay, or expected proportion. So it's basically an observed proportion minus an expected proportion, although the actual test itself gets a little bit more complicated than that. So let's go back for a second here, okay? When we're analyzing categorical variables, we're using the chi-square test for crosstabs tables, we're using it for contingency tables, and we can use it for a number of reasons when we're doing categorical variables. One thing, again, one way of using chi-square is to make market segmentation, okay? If we have two categorical variables, right, categories, that we want to test to see if there's any association or dependence on each other, then if we're looking at the dependency of categories and the relationship between categories, then it would make sense that we could use this for market segmentation. Because if you looked at the categories and you're looking for relationships between categories, what is that but building up one segment with another segment, one category with another category? So we're using categorical variables mostly for nominal variables, although there's limited reason why we couldn't also use it for ordinal variables as well. Okay? So one of the things we can use it for is to test associations among two or more categorical variables. What we're doing is we're testing the difference between proportions, between the proportions of our sample data and our hypothesized data. Okay, and we do that using this test of independence, or chi-square. The other thing we can do is to use it to see if the data fits. Is the observed proportion similar to the expected proportion? Again, these two are very much related in terms of what their functionality is. If you look at the actual test statistic itself, which you'll see here on the bottom right, it is essentially the observed minus expected squared divided by the expected. Now, I'm not requiring you to know or memorize this particular formula. However, the general gist of the formula, I think, is important. We are running a test that looks at differences between real results, or the sample, and theorized results, which would be the population. Okay? As I say here, it's comparing frequencies between observed and expected. And it's important to know frequencies because that's one of the reasons why we're using chi-square, is to use it with categorical variables, particularly nominal variables. Okay? So, if we were to make a goodness of fit hypothesis, if we were to talk about hypotheses for goodness of fit, okay, we would essentially be saying that the data fits is our null hypotheses, that the data is equal, that the proportion is equal. If the data does not fit, that will be our alternate hypothesis. So the data does not fit at least one proportion of frequencies. So again, if we were to hypothesize here with this example, the data fits the specified proportion of frequencies that we would hypothesize in the population, or the data does not fit at least one proportion of frequency. All right, so we talked about the proportion of frequencies. Now let's look at some preferences of phones. Okay, if we sampled 300 people, we find that 12 women like Apple, 108 women like Android, 24 like men like Apple, 156 like Android. And you can see that the rows calculate all out, that the columns calculate all out. And so there we have our what we call the cross tabulation table. Okay. If we were to look at our observed versus expected frequencies, what we're really looking at is a proportion of what we call the marginals. The marginals are the row totals and the column totals. And so here you see the marginals, you see them as a proportion. If we were to calculate what each individual cell was expected to be, so for instance, what the expected proportion of females who like Apple was, the expected proportion of females who like Android was, and so forth, what we would use is the formula where we multiply the row total by the column total. So we multiply one marginal here by the other marginal, and we divide that whole thing by the sample size. So you can see here, for example, that we would multiply 36 by 120 and then divide the whole thing by 300 to find out our expected frequency of females who like Apple. That is how we would get our expected hypothesized proportion of frequencies. So we would ultimately need these expected proportions because we need that for our chi-square difference test, our chi-square goodness of fit test. So we would then take the 12 minus 14.4, the observed minus expected, square it, divide it by the expected, then do it for this cell, then do it for this cell, then do it for this cell, add them all up, and then we would get our chi-square statistic. And then we would essentially use this. So the chi-square statistic is the observed minus the expected frequencies squared, again, because we can't have negative numbers in case we do. Then we need to divide it by the frequencies of the expected, and we add all of the cells up. The degrees of freedom, which we're not getting into, is for a chi-square, the number of rows minus 1 times the number of columns minus 1. So in a general 2 by 2, it would make sense that there is 1 degree of freedom. We would multiply the rows, which in this case would be 2, minus 1 is 1, by the number of columns, which again would be 2 minus 1 is 1. So 1 times 1 is 1, and that would be 1 degree of freedom. Okay? And we always are trying to assume that each cell in the contingency table has an expected frequency of at least 5. So that way that test statistic can actually run. Otherwise, we don't have enough data to be able to calculate out our expected frequency count. So again, I pitched this in terms of the null hypothesis, and SPSS will make this easier because we can look at this in terms of the alternate hypothesis and in terms of p-values or significance values. And again, if p is less than 0.05, then we would say that the test is significant, and it is significant in terms of there is some, well, we'd have to go back to our hypotheses. It is significant, which means we are supporting the alternate hypothesis, which means that the data does not fit at least one proportion of frequencies. So the expected does not equal the observed in at least one proportion. Okay, we're not necessarily sure which one, but we know that it's at least one of them. So in this instance, let's go in terms of the null hypothesis. We would look at 1 degree of freedom. We'd have to go to the table at 0.05 on a chi-square distribution table, which you can find online. If you just Google chi-square distribution table, you would find that 1 degree of freedom at point alpha or p at 0.05 is equal to 3.841. And if it was greater than 3.841, our chi-square statistic, then we would reject the null hypothesis and support the alternate hypothesis. If it's less than If it's less than 3.841, then we would fail to reject the null hypothesis and we would reject the alternate hypothesis. So it gets a little confusing here again. So let's just take it at SPSS. We'll calculate a p-value. If it's less than 0.05, then the test is significant. And again, when we talk about significance, we're talking about significantly different, significant relationship, significant effect, so forth. That's what we're talking about when we talk about significance in layman's terms. So if we looked at the observed minus expected frequencies, we squared them, divided by the expected for each of the cells, as you see here, then essentially what happens is we find that we get our chi-square statistic. This is, again, something that we don't really need to calculate, but fully out. But we find out is essentially, in layman's terms, in terms of the statistic, that we failed to reject the null hypothesis. We don't reject it. So if we don't reject the null hypothesis, again, we find that there is no significant difference. Remember, if p is greater than 0.05, then it is non-significant. And when we talk about significance, we're talking about significant difference, significant relationship, significant effect. In this instance, we're saying that there is non-significant. So there's no significant difference. We would also, or no, so there's no significant difference, so, which essentially means that if they're not different, what are they? They're the same. So essentially, that's what we're finding, that statistically, that the proportions are the same as what they should be in the population. All right. Again, the same thing happens when we use the chi-square test as chi-square test of independence. Okay, if variable A and B are independent, they are they are not related to each other. They are not associated with each other. In our alternate hypothesis, the interesting one, we say that variable A and variable B are not independent, right? They're not equal, they're not related, they're not any, right? So they're not independent, which means by logic, they are associated, or they are dependent on each other. So in this instance, if we said variable A was education, variable B was car brand purchase, okay, we would say that the null is that education level and car purchase are independent of each other. If we were to say the alternate, we would say that education level and car brand are not independent of each other, aka they are dependent on each other, aka they are associated with each other. So again, you can see how if two categorical variables are dependent on each other, or there is an association with each other, you could see how potentially this would lead to understanding market segmentations. Market segmentation. After all, if they're dependent on each other, then there must be a relationship between the two categories. Okay, so that essentially is our test of independence. That is the null hypothesis, which means that the alternate is non-independence or dependence. So we would use the same chi-square statistic. What would our hypotheses be for this? Okay. Our null hypothesis, it deals with independence. It's a test for independence. So our null hypothesis would be that gender and phone preference are independent of each other. What would the alternate hypothesis be? That gender and phone preference are not independent, aka dependent, aka associated. So in this instance, the null is that gender and phone preference are independent of each other. The alternate would be gender and phone preference are dependent on each other. Okay, so the same test would allow us to see if the variables are independent. If they're not related, then we don't have to worry about potentially using them for a market segment. But if they are related or they're dependent on each other, then this could help us formulate and look at which cells, which groups are actually dependent on each other. So it would be the same chi-square statistic, okay, is the same chi-square observed minus expected, square divided by expected, the same one. You can see there's a relationship with each other, only now we're using it to test multiple categorical variables at once. So it becomes a little bit more complicated, and not in terms of the test itself, but in terms of what actually we are testing, even though the test itself is exactly the same. Okay, so in this instance, if chi-square is non-significant, then what does that mean for our test of independence? If there is non-significant, then what they are saying is there is no significant dependency. Okay, they are not significantly dependent on each other. Right, we are supporting or not rejecting the null hypothesis. So what we're saying is that, again, we are not rejecting the null hypothesis, which means that in this instance, gender and phone preference are not related. Okay, there's no sufficient evidence that the two variables are dependent on each other at 0.05. All right, so that is chi-square analysis, okay? We're going to step back and we're going to talk a little bit about testing for differences between groups. And if we're testing for differences between groups, this gets a little bit more complicated, because what we're starting to do is we're starting to look at means and standard deviations. So we have done some stuff previously in class on means and standard deviations, on central tendency and dispersion, on the idea that in a normal distribution, that there is a center tendency, whether it is the mean or the median, or depending on what type of measurement level you have, the mode. But generally, especially with continuous variables, we're using the mean. And then we talked about how in a distribution, or a normal distribution, that data disperses around that mean, and that some distributions have wide standard deviations and some have very narrow. We also talked about the central limit theorem, that the more data you collect, the more you start to approximate the actual population mean, and you start to approximate the actual population standard deviation. Well, again, we generally do not have a large sample. We tend to have very, I guess you could call them moderate size samples, hopefully, which means that essentially we need to do is take these samples and test it against either other samples, or the sample itself, against, again, a hypothesized population. Let's go back. So frequently what we're doing is we're testing for hypotheses of the mean, because the mean is something that can be calculated readily, and then we can use standard deviations to see, in fact, if means are different based on standard deviations as well. And that gets a little bit hairy in terms of the explanation of why that is. So what we'll essentially say is what we're doing when we're testing differences between groups on continuous variables is we're testing differences between means, and in order to do that, we also are using standard deviations. So we have two different types of tests to test the means. The first is whether or not we know the standard deviation of the population. And in that instance, we would be using a z-test, because we would essentially be able to standardize the entire population. But as we know, and as we've discussed previously, the z-test, or knowing the z-test, is, sorry, not knowing the z-test, sorry, I'm a little confused because I had been offline for a bit during the recording of this. We generally do not know the population standard deviation. So because we do not know the standard deviation of the population, we usually and we do not know it, or it's unknown, we then tend to use the t-test, okay? You may have remembered this from statistics prior, okay? The t-test statistic is equal to the sample mean minus a hypothesized divided by what we call the standard error of the mean, and the standard error of the mean is equal to the sample standard deviation divided by the square root of n. Again, we're not going to go through the whole thing and how complex it is, and what the standard error of the mean is, and all of the complexities of the statistics here. What I want to emphasize here, actually, though, is the numerator, because I think it's that one that helps the most for So let's take a look at a t-test, for instance. This is what we call a one-sample t-test. And a one-sample t-test, one of the key things is that it has one population, one hypothesized population, okay? The average cost of an Airbnb in New York is said to be $168 a night. Let's just take that for what it is, okay? Airbnb in New York is said to be $168 a night. That essentially is our hypothesized population mean. We have an average cost, and it is said to be. And we want to know, in fact, if that is correct, if that is true, if the average cost is about $168 a night. So that would essentially be our mu in this instance, our hypothesized population mean that we are testing. What are we testing it against? We are testing it against our sample, which we go out and collect. So we randomly sample 25 rooms, and we find that X bar, or our sample mean, is 172.50, and our sample standard deviation is $15.40. So what are we exactly saying here? Well, if we were to eyeball it, we would say that yes, $172.50 is more than $168 a night, and it is actually more than what we hypothesized. But the problem is, don't forget, we are dealing with a random sample, and that's all it is a sample. If I go and sample it again, I might find a different average and a different standard deviation, a different mean and a different standard deviation. So I can't go out. So if you recall, we talked about the puzzle piece analogy. If I have some pieces, I might not be able to make inferences about the entire relation, or I may infer wrongly. So I can't make an absolute judgment out of that. So I need to be able to use the statistics. So in this instance, because I only have a sample, I don't have the entire puzzle. Right. So what essentially we're saying is again that we have a population mean, we have a sample mean, we have a sample standard deviation. That gives us everything we need to do to calculate the t-test statistic. And what we essentially said was that SPSS would do this for us, so we wouldn't really have to worry about it. So in any of these test statistics, what we have are estimates or our samples, and we have hypothetical values, the values we hypothesize. And what we're doing is we're dividing by the standard error. And what the standard error actually is a distribution of the errors. And again, I'm not going to get into what that actually means because this gets a little bit more complex when SPSS actually calculates it for us, and we don't have to worry about it too much. In essence, what we have found, and I mentioned that we can plug everything that we have in, is that we have the sample mean, which was 172.50. We have a sample standard a hypothesized population mean, which was 168. We have the sample standard deviation, which was 1540, and we said that we sampled 25 rooms, which was our n, our square root of 25. Calculate it all out, we get 1.46. That is our test statistic. And then again, we go back to a chart and we find what alpha is at 0.05. Because we're doing a two-tailed test, or alpha divided by 2, we would find it at 0.025, because we would divide 0.05 by 2. And then we go and we find it out, and basically we find out that there's no significant evidence at those degrees of freedom, and the degrees of freedom are t-1, or n-1, which is 25 minus 1 is 24. So what we end up finding is that at 24 degrees of freedom, the test statistic is plus or minus 2.0639, and then we go and find out 1.46 is do not reject the null hypothesis isn't in there, so it's in we don't reject the null hypothesis, which means there's no significant difference. Again, SPSS will calculate this out, and we'll find the actual p-value for this. And the p-value, again, would be kind of there is a relationship between alpha levels and p-value levels and the critical values at certain points. However, all we need to know for purposes of this class is that the p-value will tell you that there is no significant difference. The p-value in this instance would be greater than 0.05. And if p is greater than 0.05, we said that we reject the null. We fail to reject the null, but we do reject the alternate. Again, you have to start, to do a little bit of logical thinking here. If we are rejecting the alternate, we are saying there is no significant difference. So that's essentially what we would be doing in this instance. We would say there's no sufficient evidence that the true mean cost of New York Airbnbs is different from 168. So even though our sample was higher than our sample mean was higher than our hypothesized mean, we find statistically that there's no significant difference. Okay, that essentially is what happens in this instance. So this is an instance where we had one variable that we were testing on, and we had a hypothesis about that one variable, one continuous variable, and we wanted to see, in fact, does the evidence bear out what we hypothesized? And in fact, it did. Our data essentially showed that there is no significant difference, that if we were to hypothesize $168 was the average price of an Airbnb in New York, that if we took 100 samples of 25 rooms, 95 of them should show us that, in fact, it is near 100, that it is not different than 168. So let's go to two-sample t-test, because two-sample t-test now is where we start getting into differences between multiple variables or multiple groups, okay? We have a couple of different types of two-sample t-tests. What we are going to focus on in this particular course, in this particular class, and this fits with the decision tree I talked to you about, was whether there are independent samples or there are paired samples. What is the difference? In an independent sample t-test, what we are dealing with is two different populations. So I mentioned Amazon. Okay, you have Amazon has one population that sees format A and one population that sees format B. Okay, the dependent variable we said was conversion rate. So there is, in an independent sample t-test, and I'm going to iterate this again, in an independent sample t-test, they are independent. You can, if you are in one group, you cannot simultaneously be in the other group. If you see format A, you do not see format B, and so forth. So we have one dependent variable, conversion rate, and two populations, conversion format group 1 and format group 2. This contrasts with paired sample t-tests, in which you have one dependent variable, or actually two dependent variables frequently, with one population. So frequently paired sample t-tests means that there are two different measures that are related by the same population, which means that one person is measured twice. Okay. Oftentimes we use two sample t-tests to find out if there's a difference between before and after. We do something, we measure it before, we do something, see if there's an effect, we measure it after. We want to see if there is a difference statistically between before and after. So let's give some examples about how this could be used, okay? Where you're looking for a difference between two means, we're with an independent sample test, okay? Again, if we know the standard deviations of the two populations, then we would use a z-test. Generally, we do not know the standard deviation. So in that instance, we would use independent sample t-test. Now, there are two different versions of the independent sample t-test. There's when we know the standard when we don't know the standard deviation and we assume that they are equal, and there's one when we don't know the standard deviation and we don't assume that they're equal. And again, I'm not going to get into the complexities of what happens next in terms of why that matters, other than we will ultimately come to need to understand how to read a table and determine whether something is equal, whether the standard deviations are equal or not. Why does that matter? If you recall, when we talked about central tendency and dispersion, we said that, oops, let me just kind of want to, okay. If you recall, when we talked about central tendency and dispersion, we said that we could have one mean with different standard deviations, correct? We had one central tendency and different dispersions. One of the things that we're doing in an independent sample t-test is to see not only are the means assumed equal, are we testing the difference between means, but do we know if the standard deviations of the groups are relatively equal? If one is not equal, if one is smaller standard deviation and one is a wider standard deviation, then we certainly might have some issues in the way that we go about analyzing whether the means are equal or not, whether there's a difference between the groups. So again, SPSS can calculate a whole bunch of things that makes it way easier for us to deal with and just interpret the output, the SPSS output, and then again, link it to strategy in terms of marketing. So one of the things that is important that we learn to do is to read the output on this. But let's go back for a second. So let's go back to our actual tests, okay? Let's assume that we have two independent samples and that the equal variance is assumed. What would this look like in equations, okay? First of all, the assumption between assumed variances assumed equal is that we would be using a pool variance. And again, this slide itself gets kind of complicated in terms of why we use pooled variance. And a lot of it has to do with the fact that the variances are assumed equal. When we talk about variances that are not assumed equal, we're dealing with variances that are not where we have to essentially weight the variances. So again, getting a little bit more than you guys would need to understand. You should know that the test statistic is a t value with n plus 1 plus n1 plus n2 minus 2 degrees of freedom. Okay, that we are randomly sampling and independently drawing them, and we would need to have sample sizes of each group be at least 30. So essentially, we would need to have at least 60 in our test to be able to understand what's going on and make some sort of prediction with some statistical power. Okay, again, I'm going to get a little bit ahead of myself with this. The test statistic is essentially, because we're comparing groups, so I had mentioned to look for the estimate minus the hypothesized amounts, right? What we're essentially doing is we're taking the difference between group 1 and group 2, and then we're saying minus a hypothesized population mean for group 1 and a hypothesized population mean for group 2. That's essentially what we're looking at. So if you see here, there's one dependent variable, and in this equation itself, there's two hypothesized means for the population. And that essentially should clue us into what test we're using, the independent sample t-test, okay? Because the samples are independent. You can't be in one and the other at the same time. How would this work? You're a pricing manager for Wendy's. Is there a difference in prices between the burgers sold at McDonald's and Burger King? So you go out and collect the data, and you see there's a number, the sample size, 21 burgers, different types of burgers on the menu at McDonald's, 25 different types of burgers on the menu for Burger King. Sample mean price at McDonald's is $3.27. Burger King $2.53, McDonald's is $1.30 for standard deviation sample, $1.16 at Burger King. Assuming that both populations are approximately normal with equal variances, is there a difference in the average yield? Okay, so let's ask this. What we're essentially looking to do is see, are McDonald's and Burger King similarly priced? And it gets a little confusing. Again, this is why we use statistics to make inferences. McDonald's looks like it's more expensive than Burger King. Okay. The sample mean is much higher than Burger King's. It's about 67, was it 74 cents more than Burger King's is. And the standard deviation is a little bit higher as well, so there's more variance around it. So we need to be able then to test statistically whether or not these independent, right? You can't be a burger at McDonald's and a burger at Burger King. You're either one or the other. And Wendy's wants to know if there's a difference in prices, because if there's no difference, maybe Wendy's can figure out to price itself differently, right? So it can use McDonald's and Burger King, whether or not they're significantly different, to come up with its own pricing strategy. So you had this statistic, a whole bunch of calculations. We figure out the degrees of freedom, which was N1 plus N2 minus 2, which was equal to 21 plus 25 minus 2, which is equal to 46 minus 2 is 44. The whole big thing. Okay, great. We find that out. Again, SPSS will calculate out a p-value. If p is greater than 0.05, then we would support the null. If p is greater than 0.05, we would support the null hypothesis. If p is less than 0.05, then we would support the alternate hypothesis. In this instance, there is a difference between the two. Okay, if we went over to the table and we calculated where the critical values were, and we find out indeed that it would be less than 0.05. Okay, so there is a difference, evidence of a difference in means. And if there's an evidence of difference in means, then what does that mean in terms of layman's terms? That means that yes, McDonald's pricing is significantly different. It is significantly higher than Burger King's menu prices, which means if you are Wendy's, maybe your strategy is to split the difference. Maybe you want to go somewhere at $3 or at $2.75 instead. Or if you're a Five Guys, maybe you want to go fast casual and be a $5 burger. So there are implications for strategy. Okay, same thing. Independent samples, equal variance is not assumed. Okay, what happens if the variance is not assumed? Then we have to weight the variance. Again, there's a difference test statistic. And what we'll find here, I have another tutorial that deals with this as well, is that is the population of one group greater than or equal to the population of another group. How do we figure out whether or not the variances, the equal variances, are assumed? We use this equality of variances. Okay, just like anything else. Whoops, I want to back this out because it's a little difficult to see with the red hanging right over it. Okay. The f-test is 0. The significance is 0.988. Is it significant? What have we said? If it is greater than 0.05, it is non-significant. If it's non-significant, then what are we implying? That there is no significant difference. So if it is not different, then that means what? Then that means that it is equal. And if it is equal, then it would imply that equal variances are assumed. So that would lead us to read from this line instead of this line. Okay? So again, if p is greater than 0.05, there's no significant difference. If there's no significant difference, then things are equal. And if things are equal, then the equal variances are assumed. This is straight logic in terms of how to read this. And so again, we would then look at our t-test, our degrees of freedom, and it gives us a significance value for our t-test to see if the means of the groups are equal. Are they equal? No, yes, right? Again, P is greater than 0.05, which means that there is no significant difference between the groups, period. Which means that if I go back to my hypothesis, there's no significant difference. And if there's no significant difference, then what I'm saying is that customer purchase of vegetables is independent of their car ownership. Okay. All right. I have on this slide a little bit of more of an interpretation on how we use the results based on the Levene's test, which you see here, this Levene's test for equality of variances, how to determine which line we read, and then our interpretation. So there's a written version of the interpretation. The t-test results indicate the measures of the two groups have the same variances. Okay. Shoppers having a car purchase of the same value of vegetables. Shoppers having a car purchase the same value of vegetables as those not having a car. So the mean amount of vegetables that they purchase if they have a car is $10.56. The mean that they purchase if they don't have is $10.51. This is the t-value. There's the degrees of freedom. There's our p-value. It's greater than 0.05. If it's greater than 0.05, then we are failing to reject the null. We're supporting the null. Therefore, we're supporting the null. Therefore, there's no difference between the two, period. And if we go back, right, when you do these test results, you see here that it gives you the test results, but it also gives you the means. And if you calculate these means and standard deviations and standard errors of the mean, essentially, again, SPSS is giving us stuff that we could calculate test statistic, but they do it for us. Okay, but they're looking to see if 1056 is different from 1051, if the means are different. All right. Last one are two paired samples, or paired sample t-tests, okay? This is when we use the same population to test two different variables, and often the two different variables can be the same variable twice, but with one population. So we're testing the means of two related populations, and we're doing that using paired samples or matched samples from the same sample, such as repeated measures. So if you look at the test statistic again, we have one population mean mu, and we have one mean, and that is using this statistic D. And D essentially is the difference between, well, it's one person at time 1 versus one person at time 2, essentially. Okay, using n minus 1 degrees of freedom, the standard deviation of D divided by the square root of n. Again, this is called the standard error of the mean. And what we're doing essentially, again, is looking for the same thing, this mean testing for D. In 2000, so what would this look like? In 2008, all stores, Starbucks stores closed for a 3-hour barista retraining. The senior vice president of customer service wants to know if this impacted the number of service complaints. So you collect the following data. And so for each barista, there is a before, then they have the training in the middle, and then there's an before number of complaints, the training in the middle, and then the after number of complaints. The D is the difference between time 2 and time 1. And what you can see here is, for instance, 4 minus 6 is minus 2, 6 minus 20 is minus 14. It looks like the complaints went down. It looks like the complaints dropped by 21. But we want to know statistically if that is significant, right? Because 21 might not be that significant in the scope of things, in the whole realm of things. And that might only show us a couple pieces of the puzzle, but not the whole puzzle as a whole. So we use the paired t-test. We find that, in fact, the D bar, the average, right? The average difference is negative 4.2. Great, that's a little bit different than the negative 21 we had. So the average difference is negative 4.2. We could change our alpha at 0.01, so we want a little bit more of certainty. Again, we could divide it by 2 to do a two-tailed test. We're not going to deal with that right now. We find that we calculate everything out using the test statistic. We find that t is negative 1.66. We don't reject the null, which means we're supporting, or we're failing to reject the null, which means there is not a significant change in the number of complaints. So again, this is an instance where it looks like the 21 complaints difference seems like it might be significant, right? And that's why we use inferential statistics, because that 21 complaint difference ends up statistically not being different, which means that if we sampled the population 100 times, 95% of the times that we sample the population, we would come to a similar conclusion. Okay, so that means that when we eyeball these descriptives, we have a more difficult time determining whether we are seeing the whole puzzle or not. So it is important that we use inferential statistics to make this determination, to make this distinction. Okay, we're going to go with one more test of group differences. And this test is slightly different than the t-test, but again, it uses the same interpretive practice. Okay, it's the same principle, and that is we are testing for 2 or more independent groups. And we use what's called ANOVA, and ANOVA is short for analysis of variance. And this is kind of similar to what we had just done with our t-test, where we were looking for whether or not the means were the same or whether or not the means were different, depending on whether the variances were assumed equal or not. This is very similar. So what we're going to be doing is using a different statistic with a different distribution, which we call the F statistic. It uses an F distribution. So let's hop to it. In ANOVA, what we're doing is we're testing to see whether multiple groups are equal, or in terms of their population means, or whether at least 2 population means are different. Okay, our alternate is at least 2 population means are different. And when we run the test, we are not necessarily going to know which population means are different. The only thing the test will tell us is at least 2 of them are different. It won't tell us which. It'll just tell us at least 2 population means are different. And we're using this F test, okay? The mean sum of squares between divided by the mean sum of squares within, degrees of freedom. An F test has 2 different degrees of freedom. It has degrees of freedom in the numerator that deals with what we call numerator degrees of freedom, which is the number of groups minus 1. And it has a denominator degrees of freedom, which is the number of sample size, the whole sample size for all of the groups minus 1. Okay, this gets a little confusing, but what it essentially is saying that the numerator degrees of freedom will typically be small, and the denominator degrees of freedom will typically be large. The F statistic is the ratio of the between estimate of variance and the within estimate of variance. So what are we looking at? We're looking at a difference of variance or dispersion between groups versus dispersion within groups. And we're going to use the same decision rules. If p is less than 0.05, then we're supporting the null. P is less than 0.05, we're supporting the alternate hypothesis. And the alternate hypothesis, as we mentioned, means that there is a difference between at least 2 population means. Give an example. Okay. Beats Audio plans to launch a new series of noise-canceling headsets. You want to see if consumers will pay about the same price for each headset. You randomly select 5 consumers to try the 3 headsets and tell you how much they'd be willing to pay for each one. And we're going to set alpha in this instance at 0.05. We want to see if there's a difference in willingness to pay between any of the 3 groups. So what we want to see is whether at least 2 population means different. So it could be between set 1 and 2, it could be between set 2 and 3, or it could be between set 1 and 3. If we had 4, it could also be between set 2 and 4, 3 and 4, and 1 and 4, right? We want to see if there's at least 2 population means that differ from each other significantly. So if we were to look at these different sets, we could find out that each set, right, the over the ears one has a mean willingness to pay of $249.20. The earbuds have a mean willingness to pay of $226. The Beats pill has a mean willingness to pay of $205.80, and the total mean for all of the 5 people for all 3 of their sets is $227. Now, if you look, it looks like there's a difference, but is there a difference between 249.20 and 226? Is there a difference between 226 and 205? Is there a difference between 205 and 249? And how does that differ with the what we call the grand mean, the mean of means? Well, here's what would happen if we did a scatter diagram of the of everything, right? Here is X bar 1, 249.20. Here's X bar 2, 226. Here's X bar 3 with a grand mean of 205.80. And here is a roughly, a little bit higher than normal, but roughly 227. Okay. So we can derive the f-test this way. It gets a little bit complex, but it's certainly doable. You can calculate it all by hand. Certainly SPSS can give you some of the inputs into doing this, so you can calculate it a little bit more easily by hand. That's what it would essentially look like calculated by hand. What we essentially find is that we have X bar, which we already said, with an N5, X bar 2 with N2 of 5, X bar 3, N3 of 5. So our N is 15. But we can do all of this stuff. We do all the numbers out. We see, again, we need to look at our degrees of freedom 1, our DF2, and then go find it on the critical value table with degree DF1 and DF2 at 0.05, and we ultimately find it out. Great. Again, SPSS would calculate all of this out. It would find that our critical value is 3.89, and in fact, we are rejecting the null hypothesis. So what does that mean if we are rejecting the null hypothesis? Again, work through the logic. Okay, the logic says that the null hypothesis means that all means are equal. So the mean willingness to pay for sets 1, 2, and 3 would all be equal. The alternate hypothesis would be that at least 2 means are not equal. Great. If we reject the null, we're supporting the alternate. If we're supporting the alternate, then we're saying that at least 2 population means are not equal. So there is evidence that at least one of the means differs from the other 2. So that essentially is what we're doing when we talk about ANOVA. Okay. It is a slightly different way of looking at the same thing that we looked at in an independent sample t-test. It is almost the exact same thing. Okay, so what have we covered today in this lecture? And we first started talking about ways to analyze relationships between categorical variables and hypothesized versus or expected frequencies versus observed or sample frequencies. And so we said if we were looking at one variable, we can use a goodness of fit test. We use chi-square to test goodness of fit between observed and expected. If we have 2 or more continuous variables, we can use the test of independence, again, to see if there is a dependence or independence between the 2 continuous or 3 or 4 continuous variables. Okay, I'm not continuous, sorry, categorical variables, right? And we're sort of typically using chi-square when we use categorical variables, period, okay? We then moved from chi-square into talking about t-tests. And so we went from our one sample t-test where we were comparing a sample mean to a hypothesized population mean, which we frequently do. We then went to an independent sample t-test where we talked about one dependent variable, one dependent variable with two different populations. Okay, so we're comparing the means of independent populations, and if the populations are independent, that means you cannot be in one group and then be in the other group as well. They are independent of each other. And then we talked a little bit about the difference between equal variance versus unequal variance and how to read that. And then we talked a little bit about paired sample t-test or paired t-test, where we have one population on two dependent variables, and frequently those two dependent variables are can be related. So frequently we use it for before and after, or what we call repeated measures. Okay. The third thing we talked about is we talked about ANOVA, or analysis of variance, and we talked about comparing the means of two or more groups. So analysis of a variance, or ANOVA, tends to function very much like an independent sample t-test. Okay, and that's essentially what we've talked about. In our next lesson, we're going to talk a little bit about correlation and regression. Correlation essentially is looking at relationships between continuous variables and seeing if they are related. We've talked about spurious correlation in the past, but we need to test correlation. And then we also talk about regression, which is the looking at the effect of variables, continuous variables, on dependent variables. We can look at multiple continuous variables and their effects on a particular dependent variable. So that's it for now, and we'll see you next time.